Hey guys, so welcome back to your next class. So in the previous class, we were going through what exactly is the movement of this thing like, right? Electrons in a conductor. Right, so today what we are going to do is we're going to figure out if these electrons are moving, how exactly are they moving, right? We figured out that how do we measure current based on how many charges are moving and how much time. Now, since we spoke about movement of charges, when we speak movement, one question that will always get raised is what type of movement is it? How fast is it? Which direction is it in? Right? Because that's not something that we have discussed. Right. So we only saw that it moves. We didn't ask these previous questions, and that is how fast and which way or which direction. Okay, we'll try to answer these questions today. Okay, now when we talk about electrons moving inside of a conductor, one thing that you need to think about is, are the electrons moving like continuously freely, right? Are they like just, is it like an empty road for them that they just like zoom, go really fast in it, or is there like a lot of congestion? That's a good question to ask, because based on that you'll figure out exactly how fast or how slow they are going, right? Meaning if there is a lot of congestion, it means obviously they're going to go slow. If it's more, if there's more space, they can go fast. Right. So to figure this out is quite simple. If you remember, we spoke of electrons coming out of the metal atoms, right? We said that they live inside of a lattice structure, which is nothing but like interconnected ions, okay, which is made up of nothing but metallic ions, right? Metal ions, right? And these electrons are moving around and through these ions. Now, if that is happening, what do you think? Is there like a lot of space, or is there not a lot of space for the electrons to move? Okay, obviously there will not be a lot of space. Okay, so when you look at electrons moving inside a conductor, it'll never be like a simple straight path. Okay, because there is a lot of obstruction in between. Okay, it's more like it's gonna keep bouncing around different things. Because of like the obstruction, it'll hit something, then it is going to slow down and go off in another direction, hit something else, go in another direction, hit something, slow something. But the reason why they'll keep going towards that one direction is because of the power source that we put, right? We have this battery or something attached. So it doesn't matter how many times the electron is hitting into another atom and slowing down. The moment it slows down, it will get speed up again because of that very power source, that battery, that something like we drew like this, right? Yes. So that source of power will definitely keep on pushing the electrons towards their direction which they're supposed to go. Okay, now since this is all random and we cannot tell which electron is going in which direction, we just assume that all of them go towards it in a straight path. Okay, so instead of calculating their exact velocity, we will calculate something called their average velocity. Okay, average is just like an average estimate, which would be roughly the similar for all of the electrons inside of the conductor. Okay, so this is also called as drift velocity. Okay, since the electrons are moving, we call them drift velocity also. Okay, so essentially we are calculating something called the average drift velocity of these electrons. Okay, that will tell us how fast they are going. So now to measure this, how do I do it? Okay, so let me assume that there is a conductor like this. Okay, I'm going to take like a small section of this conductor. Okay, if you remember, this is a wire, like it's three-dimensional. right? So I'm taking like a three-dimensional shape, like a cylinder, part of this conductor. Okay, I'm going to measure how fast the electrons are going through this. Okay, assume that this area is A. Okay, uh, A. So, so we are going to measure the number of charges within this entire area. Okay, so what I can do is within this cross section, I'm going to see how many electrons can fit. Okay, so I will say uh, if n number of electrons are there, okay, within an area of A, then total electrons can be, we need to look at the volume, correct, because it's three-dimensional. We can say n into A. Okay, number of electrons times the area. Okay, this is the entire space that we are looking at, and this would be the cross-sectional area. So in this whole volume, we can get n into A electrons. Okay, now what else do we need? Okay, we have something called current already. All right, so what we can do over here is there's a formula that says I equals to n into A into, we have number of electrons, we are also going to take what is the charge of each electron, okay, into the velocity, okay, which is nothing but the drift velocity. I'll write it as V. Okay, measuring the current. Okay, you don't need to know the entire process here, just remember the formula. Okay, I equals to n q a and vd, drift velocity. All right. So if I have to measure this out, I want to find out what is this vd. Okay, so I'll say vd equals to I divided by nq into a. Okay, now what I'll do, I'll take this I as 1 ampere of value. Okay, so I'll say I equals to 1 ampere. Okay, now we need to figure out what is this n, q and a. Q we already know, which is nothing but 1.6 into 10 to the power minus 19. Right, that is the charge of one electron. We need to figure out what is n, and we need to take a certain value of a, which is the area. Okay, so I'm going to take an area of 10 power minus 6 meter cube. Okay, if we take this much area, we need to find how many electrons are there in copper. Okay, we call this as electron density. So an experimental value is there for this, which is 8.5 into 10 to the power 28 meter cube, meter per meter cube. Okay, all right. Now what we are supposed to do over here is simply substitute these values. Okay, I will not get into the calculation, I'm just showing you so you know the process. Okay, main thing you need to remember is what is this and what will the answer that's going to come out look like. Okay, so if I have to find out VD, it will be 1 divided by 1.6 into 10 to the power minus 19 into 8.5 into 10 to the power 28 into 10 to the power minus 6. All of this, if you simplify, we'll find the drift velocity of 0.07 millimeter. Okay, 0.07 millimeters. This is how much the electron is moving in every 1 second. Okay, now 1 millimeter you have seen on the scale, right? On the scale you see 1 centimeter, divided into 10 parts, with each of them is 1 millimeter. Not even 1 millimeter, it's moving in 1 second. 0.07, meaning you divide it into 100 parts, that 1 millimeter, and out of those 100 parts, only 7 parts. Imagine how small that distance is. In every second, an electron is only moving by that much distance, right? That is not at all fast. In 1 second, you can move a lot, but the electrons are moving just like tiny bit. Okay, that is very surprising, you'll see, because if the electrons are moving so slowly, how come electricity works so fast? At the moment I turn on the this thing, my fan is on, my lights are on, everything turns on in a second, within like seconds, like whatever fraction of a second. But how is that possible when electrons are moving so slow? It's simple. It's because electrons are all over the conductor. There are electrons just within the tube light or within the fan or just beside it, right? So they are closer than we think, right? Because of that, the moment you turn on the switch, they'll keep flowing right from where they were stopped before. Okay, so that is why they work pretty much instantly. All right. Now, this is the speed of electrons we figured out. Now, what is the direction of this current? Okay. Now, we know that because of this power source, there's something called an electric field that is set up, right? Now, we'll talk a little bit more about electric field. It goes in a certain direction. Okay, it goes in a certain direction, which is from positive to negative. Okay, it goes like this. All right. Now the question is, if it is an electron moving, does it go in the same way as the electric field? Okay, the answer is no. Okay, it will go in the opposite direction. Simple reason being is because of its negative charge. Okay, depending on the charge of your particle, you can tell what will be the direction of your movement of that particle. Okay, if it's a negative particle, it moves opposite to the electric field. Okay, and if it is a positive particle, it will move in the same direction as the electric field. So if my electric field is clockwise, this is clockwise, then my electrons will move in this direction. Okay, they are always opposite to each other, or we say electrons move against the electric field. Okay, doesn't matter which way it is, it's always going to be the opposite direction. It's like, think of it like this: there are people coming towards you and you're going towards them. Okay, there's a crowd pushing towards you and you're going through them like a hero, right? So think of it like that. Okay, this is the electric field, this is the electrons going through them, and if you start running with the crowd, that is a positive charge. It goes in the same direction as the electric field. Quite simple. Okay. This is just semantics. It's a little bit theoretical, but it's fine. You'll understand why this is like that once we actually get down a little bit more ahead in the chapter. Why exactly are the electrons moving in that direction? Why not with the electric field? Okay, we'll take a look at that in the next class. As of now, I'll stop here. I hope you understood. Again, like I said, only a few things to take away, major things. What are the formulae that we used? What are the values that we got? Okay, the direction and the speed values. Okay, so I'll see you in the next class. If you have any questions, please drop them in the comment section below and we will continue the next class. All right, thank you so much.